What's going on, people? How are y'all doing today? What am I going to talk about? I mean, last video I mentioned that I was going to get into mitochondria, but I said before we even go that deep, there's a question that needs to be answered. And what is that question? The question is water. Agua, H2O. Like, I get questions off water more than anything. It's one of the most confusing substances, but the most plentiful that exists. We all play in it in the summertime. We need it in ice form to cool us down. 90% of our body is made up of it. 90% of the earth is made of it. It's like, what is the secrets and what is the big deal about water? What type of water do I drink? And really, what is this molecule? So I said today I'm going to dedicate my energy to getting you to understand just how serious this water really is. Because I don't think we really understand that we're living in a heavenly environment where there is an influx and abundance of this molecule that is a necessity for our survival and our living. All right? Now, before we get started, I want to give love and light to Mona Harrison, who transcended some years ago. Mona Harrison, for those of you who don't know, I was introduced to by Minister Inky. This sister right here is really the one that started the movement on water's hidden properties. You hear a lot of other names you're going to hear in this presentation: Gerald Pollack, Masaru Emoto, Mai One Ho, all these individuals that deal with the science of water, but you never hear about Mona Harrison, who actually transcended under some weird circumstances. So look that up. However, she's really the first one to really come through in this modern day in regards to the hidden properties of water. So we're going to give love and light to Mona Harrison. I asked all y'all to check her out. All right, so when we look at water, what is it? It's a molecule, which means it's made up of atoms. And atoms are what? These elements that have a orbital of electrons around it, depending upon how many electrons they have, that's usually the number. So when you're dealing with hydrogen, it's a 1 on the periodic table of elements because it got 1 electron. And oxygen is 8. So what we're looking at right now is a bond, hydrogen bond or a covalent bond going on between the atoms of oxygen and the atoms of hydrogen right here. Now the reason why you have pluses, okay, and you have minuses here is because we got protons with a positive charge, electrons with a negative charge, but hydrogens only have 1 electron. So they're sharing that with the oxygen. And in doing that, it's giving its electron up, so to speak, so it's predominantly a proton type energy now. So both these hydrogens represent an overall positive energy, while the oxygen is getting all types of electrons. It's filling up its orbital, so now its charge is predominantly negative. So the D that you see on here is for delta, and delta stands for dipole, and dipole means positive, negative. Just like a magnet has a north and a south, and the opposites attract and the same repel, it's the same properties here. Okay, except what you see is a positive charge coming from the hydrogen in here, all right, and then the negative charge coming from the oxygen. Okay, now how many phases of water and how many states of matter? Because when we were coming up back in my era, in the last age of enlightenment, it was 3 states of matter, it was 3 states of water. It was liquid, solid, and gas, and it was ice, right, and liquid, water, and vapor, and that was it. But now there's 4 phases, okay, or 4 states of matter, and the 4 states of matter are solid, liquid, gas, plasma. The beautiful thing about water is water mirrors the states beautifully, where the ice form of water right here, where you see the atoms are kind of slow and they're in a regimented structure. The liquid form of water, as we know in the oceans and the lakes, have more of a string of pearls where their bonds are constantly breaking and reforming in a fluid motion. The gas or the clouds that we see in the sky, that form of water, are the atoms moving all around rapidly, not really connected like these other two. But then when you deal with plasma, like in a flame or in lightning, what you're dealing with is that atom, the positive, the negative of the electron, the positive, and the neutral of the neutron in the core. They all separate, and these subatomic particles are on their own the same way that the atoms are on their own in the gas stage. So it's kind of like a gas phase of gas. All right. Now, water mirrors this exactly, as I said, with the liquid being like liquid water in the rivers, solid being the ice and the glaciers, gas being the vapor, like when you see clouds, all right, or mist or fog. And then you have the super cool structured or the easy phase of water, which would represent the plasma. And you got to keep all these things in consideration when you remember that our body is predominantly water. And dehydration is usually the onset of all diseases. That mucus that Dr. Sebi talks about coming up usually takes place after the events of dehydration in the body. That's the only thing that's going to cause your mucus lining to get thick, okay, and more viscous. All right, so we all know from Masaru Emoto, who transitioned not too long ago as well, that he did studies on water and showed that through the intent of positive energy and love, you'll get a structured formation of water based on its atomic, its molecular structure, combining in a hexagonal lattice, where if you impart hatred, pain, or fear into water, it has a non-symmetrical shape, that of just pure chaos, okay? So you have to keep that in mind with your thoughts, as well as the foods and the things that you eat, or that you visually eat, or that you mentally eat on a daily basis, that will influence what? The state that your water is in inside of your body. Okay, your eyes is all water. All right, so alkaline and acid, acid and alkaline, people is all about going alkaline. Why? Because Dr. Sebi talked about getting alkaline in the 80s because it was so far off on the acidic side. Now, these days, everybody's coming into this information by way of YouTube and Instagram and sound bites and things like that. No one is getting the whole story. So a lot of people don't get the whole alkaline acid thing. They think if they drink a lot of alkaline water and if they Google alkaline acid on the internet and then they pull up the images, they just eat those foods and just drink that alkaline water to get super alkaline, and then, you know, you're a walking Duracell and you're good, right? No, you're not going to be good, because bleach and ammonia are alkaline as well, all right? And there's a balance. Matter of fact, our body is maintained slightly past neutral. Really, we're more of a neutral body, slightly towards the alkaline side of the chart. We're talking 7.35 to 7.45. If it drops below that, we're talking acidosis. We'll get in, and if it rises above that, we get alkalosis. So this is the chart, all right? The reason why it's called pH scale is because it's parts hydrogen, same hydrogen that's in water. So acid and alkaline is usually perceived by way of water as a universal solvent, all right? When you look at the 7 here, that's the neutral, just like the neutron of the atom, or the axis in which everything spins around, while the acidic is to the left in a negative. All right, every number that you see is a magnitude of 10 lower than the previous number in regards to its hydrogen density, how much hydrogen is inside, because water is H2O. All right, so hydronium would be a H, or a hydrogen that is not associated with the H2O anymore. It's on its own, and if there's a concentration of hydronium more than hydroxyls or OHs of the entire H2O, you get left with acidity. But if you increase the oxygen content, as he would talk to you, get oxygen in alkaline foods, you have more OHs, okay? And when you have more OHs, you have more of an alkaline side. Acidic gives up electrons. It's an electron donor, gives them away, while alkaline is a receiver. It's receiving the electrons, okay? So what we want is we have a system to receive electrons so it can conduct the electricity. We don't want a system that's constantly giving electrons up, because then that means we're giving up charge and giving up energy. So that's the basis of acid and alkaline. But you need a balance of that in your system, like an 80-20 or 70-30, because your hydrochloric acid is acid, and you need that to break things down in your stomach before it goes into the intestines. So understand these properties, and as we move forward in this whole water thing, you'll understand how pH plays a very important role in charge distribution with our body, okay? All right, so easy water, the plasma form of the water. Easy stands for the exclusion zone, okay? This was made popular by Gerard Pollack, all right? And if we look at this schematic right here, this represents a hydrophilic surface, water-loving surface, all right? And this is the water that's sitting against the surface. And what ends up happening is when infrared energy from the sun, from ambient light, hits, we're talking electromagnetic radiation, hits the water, specifically infrared, it increases the layers of exclusion zone, which is predominantly a negative charge. Why is it called exclusion zone? Because protons or positive charge is being excluded. It's getting excluded away. So if I'm excluding all the positive charge, that means that leaves negative charge. All these layers represent negative charge. All those layers represent electrons. So we have a space that's predominantly negatively charged, and we have a space that's predominantly positively charged. Okay? This is the hexagonal easy water sheet. So if you can imagine, like graphite or like ice is a lattice, a hexagon shaped lattice stacked one on top of each other. It's like we're looking down, bird's eye view, at the lattice structure. And if you look right here, that's a hydrogen, that's a hydrogen, that's an oxygen. So the small circles are hydrogens, the large circles are oxygen, and it forms this particular structure. So when water has a structure, it becomes way more coherent, and its electrochemical properties that it contains, its photochemical properties that it contains, becomes easier to utilize. Okay? Now, to give you another example, the surface that I showed before of this chunk, now let's imagine it in tube form. This material is called naphthion. Naphthion has a hydrophilic surface, hydro meaning waterphilic, meaning loving, so loving water. If we blow this a section up, we see that's the hydrophilic material. This is the exclusion zone. Look at all that negatively charged, and look at this area where all the positives are. So imagine this as one of your cardiovascular vessels. Imagine this as a capillary. Imagine this as a tube in your body. That would mean the flow of water is going through this tube. You see the negative charge here and the positive charge there. Well, red blood cells have what? A negative charge, so they're going to stay in the center area, flowing with all of this positively charged water, while the negatively charged around the edges here is going to prevent the red blood cells from clinging to the walls, and the negative charge from each red blood cell will keep themselves from clumping into one another, bumping off each other, creating velocity so that your blood can flow. All right, but you can clearly see here that all the water in our system going through all these tubes are able to orient the positive and the negative charge separate in order to create what you would know as a battery. Okay? So when you have a positive charge, negative charge, an anode and a cathode, and the flow of electrons between these 2 points, you have electricity. And this is how we're able to create energy in our body. We're light bodies by way of the sun. The sun hits our water divides these charges. These charges is what fuels our system. Okay? So to give you an example, this is a water battery where you got a positive, negative charge. We have these plates inside, and what ends up with usually are zinc or copper, and there's water in here, but there's also a dye that's added, and the reason why the dye is added is because the dye is pH sensitive, all right? Which means that if the movement of acid and alkaline occurs in this water, we can now see it because there's a pH sensitive dye. So when they put this in there and they added the infrared, they ended up seeing that the low pH, the high pH separated in this water, and when they ended up removing the battery, they was able to put a light, and the light was able to come on by way of the charge separation that occurred as the solution of water. All right, so this is what we're able to do in our body. If we understand that water is our power along with the sun, carbon being a semiconductor, which we will be getting shortly, this is why carbon plays such a huge role. All right, so the main source of electromagnetic energy on Earth is the sun. The sun hits the water, the infrared energy imparts on the water. Everywhere there's a surface, there's a predominantly negative charge where there's bulk water inside. At any given time, when you look at a glass of water getting hit by infrared energy, 40% of that water is predominantly electrons, okay? Highly organized, okay? All right, so this comes into effect not just through the cardiovascular system, but the microtubules that make up the skeleton of our cells, all right? And also through cartilage, all right, which is also carbon-based. Remember, these are made up of tubulin, all these little sections, these purple and light purple, purple and light purple, are like little beads that come together to make this cylindrical straw-like structure, and they're made up of amino acids. And remember, amino acids are made up of what? Carbon. These are carbon complexes. So this is all carbon, all right, like a carbon nanotube. And cartilage is made up of a 3-strand helix, like a braid, of also amino acids that are carbon-based, and this also is reminiscent of a carbon chain, all right? And this carbon chain, we're going to see how it interacts with the water as well, all right? Another thing we need to understand is we think of currency as electrons moving, right? But guess what? There's also something called positive currency or proton jumping, meaning when we have water in our cells and in our body, then what we can do is kind of like a hot potato game being played, where if you notice right here, these are chains of water, okay? H2O, 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 they linked, okay, by these hydrogen bonds. Here's a hydrogen. The hydrogen comes, it attaches to the oxygen and releases this one, and then each one gets knocked to the next, kind of like dominoes, all the way up. So it's almost like a wave can occur. So if I have water in my toe, this is a way that whatever signal from my toe needs to get up to my right shoulder can get there because of this proton jumping mechanism that occurs with the organized water that's inside of our system as well. Okay, so here's another schematic, okay, just to show a negative electrical voltage zone, a positive electrical voltage zone, and then H, okay, the 2 hydrogens right here, what? Drawn to the negative side, while the negative charge of the oxygen drawn to the positive side, okay? Now, to get a better understanding of semiconductors, all right? N-type semiconductors have a larger electron concentration than hole concentration. The term N-type comes from the negative charge of the electron. In N-type semiconductors, electrons are the majority carriers and holes are the minority. Okay, now as opposed to N-type semiconductors, P-type semiconductors have a larger hole concentration than electron concentration. The term P-type refers to the positive charge of the hole. In P-type semiconductors, holes are the majority carriers and electrons are the minority carriers. Now what am I talking about? Well, if we look at the periodic table of elements and we look specifically at group 14, you see things like carbon and silica. You always see how carbon and silica are interchanged as a base life form, right? But we're going to focus on carbon right now because that's predominantly what we are. Well, if you look to the right to group 15 and you look to the left to group 13, what you will find are doping agents, okay? And doping agents are other elements that you can add to semiconductors that increase its conduction capabilities, makes it more refined. They're in all the electronic devices. So if you look here in carbon, you see nitrogen here, which in amino acids we see nitrogen. In chlorophyll you see nitrogen. In hemoglobin you see the nitrogen surrounding the metal, okay? Now, one of the number one doping agents that we usually use is phosphorus on silica when it comes to what? A photovoltaic cell, a solar cell, okay? So we can see these same properties happening in our body when I show you that microtubules, okay, are carbon-based and collagen is carbon-based, okay? And then they are doped with what? With minerals, okay, that are inside of the amino acids and the molecules and the enzymes along with this water, creating this semiconductive kind of quantum mechanical effect that occurs where we're able to use light and water in order to perpetuate this wonderful system that we got here. So once again, group 14, all right? Now, depending on 13 and 15 will be whether it's an N-type or it's going to be a P-type. The N-type or the negative type one is going to be group 15, such as the phosphorus on the silica, okay, or even this nitrogen on this carbon. But if you want to talk about P-type, then you'll have boron, okay? Boron ends up being on the silica, all right? So what do we mean by the P-type and the N-type? And I'll go back there real quick so we can understand, all right? So here's an N-type and here's a P-type. When you dope it with another element, that N-type element that you doped it with got more electrons than the elements that's already there. Because it has more electrons, it's uneven. It's not going to be stable. This electron is going to look to flow. Okay? P-type is the opposite, where you have an element that has less electrons than the one here. So what does that mean? There's something missing. There's a hole. So that's the difference between the N-type and the P-type. That is the type of elements that we have working in our body, and we're talking about the daisy chain. Okay, that daisy chain that I showed you with these hydrogens right here would be similar to a P-type, where these holes are getting moved. Okay, all right. So here's an example right here. Okay, carbon is a diamond, so that's more of an insulator. Insulators are elements, not elements, but materials that don't allow current to go through, such as rubber, around a wire, like when you plug in stuff in the wall. Okay, but that's it in diamond form. But in graphite form or graphene form, okay, of carbon, where the interatomic spacing is larger, making the band gap smaller enough, guess what? It supports conduction. So depending upon the atomic arrangement of the carbon will determine whether or not it's an insulator, or it can be seen as a semiconductor that can then be doped by either N-type semiconductors of the following group or the P-type semiconductors of the previous group. All right, so to give you another example, P-type, N-type, okay, the white represents holes, the black represents electrons, okay, the combining of electrons and holes depletes the holes in the P region and the electrons in the N region near the junction, okay, so you're seeing that there's a flow of electrons that's occurring, but as they flow, they leave holes that need to be occupied. Those holes that need to be occupied represents that P-type semiconductor, where these particular electrons that are constantly flowing or moving throughout the metal or whatever the conductive material is represented as the N-type. All right, and you can see this in the cellular membrane with the lipid bilayer, and we have sodium with that positive charge, and we have the potassium. It has a positive charge as well, but then there's a membrane potential difference that causes this outside here to be positive, but the cell to be overall a negative charge. And that allows and that determines what solutes, what minerals, which things are going to get in and out of that cell. But you can mirror that over to what? The P dope, the N dope that we just talked about, with those different layers, with there being holes and there being actual electrons. So that represents a source of energy, and that represents a vacuum kind of space that is receiving. Everything is about an acceptor and a donor, somebody giving something, somebody receiving something, and our whole system is a reciprocatory process that keeps occurring with electrons. All right. So just to give you another example, silicon is the big gray, the little ones are electrons, the black, the phosphorus is one of the doping agents, the boron is another. The boron has less electrons, so it creates a hole, overall positive charge, so it's a P-type semiconductor, where the phosphorus is an N-type because it got more electrons, and because it got more electrons, it has a negative charge. All right, and these are the two types right here that exist inside our body. Donor impurity atoms have more valence electrons than the atoms they replace in the intrinsic semiconductor lattice. Donor impurities donate their extra valence electrons, that means the electrons in the outer shell, the outermost, okay, highest state, to a semiconductor's conduction band. That's the band that allows the flow of energy to occur freely inside a material, providing excess electrons to the intrinsic semiconductor. The intrinsic semiconductor is the original material, the silicon. The extrinsic represents its properties once it gets doped, okay? Once it gets doped, which I find ironic, all right? Because of dopamine. Excess electrons increase the electron carrier concentration of the semiconductor, making it N-type, okay? So these are just the principles. Once again, this is another image that gives you a kind of understanding. So if we look at this right here, this is a microtubule, and this is actually showing the ion wave propagation based upon the charge distribution of the microtubules. And here is also an example of the daisy chain, hot potato, proton currency that I was talking about earlier with the with the water molecules. Okay, these are H2O molecules right here, shooting or knocking protons along this one string of water molecules that are linked in order to create what signal or an energy transfer that ends up occurring. All right, this tight space inside this microtubule, because it's so small, is what really enhances the properties of water and its quantum effects. All right, this also explains why when you add salt to water, you can get combustion. Okay, y'all can look this up. Okay, and this is based on coherent domains inside the water, where when there's a salt solution with water and you add electromagnetic energy, guess what? You can yield a flame or a fire. Okay? And these are microtubules right here, just to give you an example how important they are in the cell. They're responsible for cellular replication, where the chromosomes line up in the center and the cell splits into two. These are the mechanisms that allow that to happen. Okay? Now, this is also something very interesting, where ATP is always seen as energy. ATP is used to unfold proteins to allow their amino acid residues and their charges to be exposed to the surrounding water, so the negative positive charges of the water align on the proteins and create what we call polarized multilayers. Potassium attaches too. This is what the potassium is for, and this allows the water in your cell to change states from a viscosity of a fluid liquid to that of a gelatinous structure. Why you can't just wring water out your arm is because you're in a gelatinous structure based on these polarized multilayers. All right. Now, lastly, coherence domains. Coherence domains represent 40% of the water. What are they? They are 100 nanometer spheres that contain highly organized H2O molecules in there that can contain or utilize electromagnetic radiation in a very, very powerful manner. All right, you could look more into that from Emilio Del Giudice and Mai Wan Ho, but this represents something called cyclotron resonance, where you use two magnets north and south in order to pin a current in the center on these little D-shaped discs, and as a current starts to flow around here, the alternating magnetic field causes it to keep turning at an angle, which makes a spiral, and it spins until it gets very fast, and then they can fire it. Well, your body can do that as well with the coherence domain that's inside of water. Okay, and the funny thing is, the system uses this in order to incite diseases, because they can put something in the water, hit us with electromagnetic radiation, and then it comes, to be. So which water? Steam, distilled water, clouds. Why do I speak about distilled water? Because that represents neutral on the pH scale, no doping agents. Mountain spring water is electrolytes. Okay, coconut water, which used to be used as a drip back in the day, is one of the best examples of our plasma. So I suggest people drinking, one of these three waters. If you got access to a spring, that's the greatest. KT the Arch Degree, Instagram and YouTube, Kamani Tate on Facebook, lovegreenlife@gmail.com for inquiries, and the new product display is Renalite, because the kidneys is all about what? Splitting and taking care of the water of the body. Peace.